Too?
Yes.
Okay.
So
I just have to rename.
will it work if we just put the microphone in the middle?
Yeah, you can also hold it closer to you, but otherwise it works. Yeah, if it's you have to lay it down, I think, because.
Live.
Yeah, so it works. How could I call your talk or topic? How does internet work?
I'd say the underlying infrastructure of peer-to-peer networks. I'd say something like that.
Let me see how your audio sounds, because you have a very.
Oh yeah, I'm not loud. I'm very quiet. Yeah, okay.
I think you're audible.
Okay, good. So yeah, earlier we were starting a discussion about a very common area that's ignored by developers of peer-to-peer systems and protocols, which is the infrastructure that all this relies on, usually the internet. And that when those protocols are designed, they assume that each peer in the network are directly connected to each other, and that the way that information flows from one peer to another can be abstracted, and whilst there is a very complex set of systems and PCs and protocols that allows that, and so we started shedding some light on what actually happens below the level that we usually start working with peer-to-peer systems. That sparks a question. So how do you folks think of the underlying systems that are used for peer-to-peer networks? How is it shaped, and what are the assumptions that you make when you design peer-to-peer systems?
Sure. I'm gonna be a straw man, basically. I'm gonna pretend to be a blockchain networking dev. So in my network, I need my core block producing nodes to communicate with each other directly. So what I do is I establish connections between them. They have other connections to handle communication with the outside world and take transactions and stuff, but I make direct connections between my nodes. There's they're meant to be geographically distributed, but in general I want all of my block producing nodes to connect directly to one another. So I assume that when I make a connection between my block producing node and my other block producing node, it is a direct connection, and it goes off to the ISP, and somehow that connection goes directly to the other block producing node, and and there's nobody in between. That's just a direct connection. Maybe we do some encryption to avoid eavesdropping by the ISP. And that's my understanding of how my nodes communicate with each other.
Yeah, and when I'm using hypercore protocol, I imagine, yes, I'm a peer, I have my hypercore, I log my data to that hypercore, and then I join DHT, distributed hash table, and this matches me with other peers, and then we can just send data directly, because it's also local first, so it kind of shouldn't need an internet service provider. So, but on what is all this based? I usually just, it's like plumbing. It's working, it's there. I don't know how exactly it works. But maybe just a few words of like, what is your background, so that like if somebody is following, can understand like where are you coming from.
Yeah, fair enough. So I do work on internet engineering project, so internet working as a field. So I work with and for ISPs of various sizes and network operators that are not necessarily service providers, internet service providers, in establishing their network edge. So what happens when data information leaves the network and joins another network? Because as you probably know, the internet is a network of networks. It doesn't connect directly, like computers directly between one another. It connects networks between between each other. So I've spent more than a decade working on these issues, so I have a pretty clear vision of what happens under the hood of the internet, and what allows TCP/IP to work reliably enough that we can assume that communication is working just as if it was working between peers that are directly connected, which they are not.
Spoiler.
Spoiler, they are not. So yeah, what I would like us to do is to explore those pipes, this plumbing, by going down the stack layer by layer, and breaking these assumptions and replacing it with actual observation and design consideration, and understanding of actually how the magic is made, because there's no magic in there. It's
I mean, it's magic for us because we don't understand it.
Yeah. So let me rephrase, like paraphrase what we just said, is that the peers on an internet protocol network maintain, like the network maintains the illusion that peers are directly connected in a way that each node has an address and has the ability to send a packet over the network using a protocol like UDP or TCP that will allow that packet to be routed to the node that has the destination address. Just on the layer that we've been discussing, there are mainly two protocols that we use, which are TCP and UDP, which have fairly different properties and are different in a fundamental aspect, which is what we call their reliability. So TCP is a reliable transport, and UDP is not. But it's there's a precise definition of what we call reliable. It's not just like it works well. So with TCP, you'll be able to establish a connection. A connection is an abstraction that it represents a flow of packets, like a pipe, that is defined for the length of what we call a session. After the session is initialized, that protocol TCP allows each participant to communicate reliably in a way that when they send a packet, they will know whether it has reached its destination or not. So they will be, they will be notified that the destination has been reached and that the packet has traveled all the way there. So the way it works, we'll not go too much into detail because it's not very important to this discussion, but the way it works is that TCP has defines what we call a handshake. That is the initialization of a session. And then once the handshake is completed, so that's a predefined exchange of a certain information that is necessary for that session to be established, then it will define a set of information that will be sent in band with the actual data that's called acknowledgements. So that's the part that we are interested in. There are other informations, but like flow control and ways the ways that we use to avoid congestion. But that's not really important for what we're talking about. The acknowledgement is what's important for that. So
inside the pipes, you get some like lubricant and some like
no, like see it as, for instance, you send
antimicrobials,
carrier pigeons back and forth a route, and
it's like a border crossing at each end.
Yeah, so you will attach some information that will say the last message that I received was this one.
So it's referencing messages.
Yeah. So
is that to prove authenticity?
No, it's just to notify the sender that a certain amount of information has been received.
So it's acknowledgement that the message was received.
Yeah.
Okay.
So it doesn't secure the communication at all. It's just that
you're aware the communication has happened.
Yeah. So that's what makes TCP reliable. So it doesn't make the packets magically teleport to the destination in a way that's absolutely certain. It just has a back channel in band that
feedback or like loop that you know that it was like tracking in the post office.
That's it. That's exactly it. It's just that so TCP flows are bidirectional. So it allows to send data both ways. Once the session is initialized, both participants can send data towards the other, and the tracking information is basically sent with the next packages, if you will, the post. So when you receive data that the other has been sending you, it will also have tracking information for the data that you have sent previously. So that's.
I don't know if it's like a good idea to bring this up now, but like what you're explaining is kind of like bringing up another talk that we had earlier about hole punching. And it wasn't
how to make a handshake with through the firewalls. If the firewalls are blocking, so you send a lot of packages.
It wasn't exactly clear to me. I don't know if you're aware of what they do, but it wasn't exactly clear to me because they were saying like, oh, they make sure that like the they make sure that they can get through a port by just broadcasting packets on all the ports.
Yeah.
To me, that sounds like UDP.
Yeah, not hole punching relies on UDP.
Yeah, but can you do like send packets using UDP and then establish a TCP connection?
Can we then just learn what is UDP first?
Okay.
This was TCP.
This was TCP. So that's by far the most complex of the two. UDP is the so TCP is transmission control protocol. It allows you to embed data that is control information about the session. and UDP is the user datagram protocol. So it allows to send data in a way that's not reliable, that is fire and forget. So you have no way within the protocol of knowing whether and when the data has reached its destination. Just rely on the goodwill of the intermediaries to relay your data. So that does not make it an inferior protocol to TCP.
But it doesn't have tracking system.
Yeah, exactly. Exactly, and so it doesn't require a session to be established. So that's a huge advantage because, like you hinted towards the limitations brought by NAT and the need for hole punching. You don't need that with UDP because there's no session.
Yeah.
Just send the data to a predefined port.
Or all of them.
Yeah, all of them. Which and in the hope that it will reach its destination, but generally, and that will probably hint into the next step in our exploration, in that the internet. So that what's below all that is. I don't want to use the word reliable because it has a precise meaning that we defined, but it is working well enough that you can assume that most of the traffic that you send will actually eventually reach its destination.
And this is what it means, reliable, or does reliable,
reliable means
is just if
means
it's tracking?
you know when it does.
Yeah.
And so you can TCP also defines what we call retransmissions. So if a packet has not been acknowledged, so if there's a hole in the stream, you can then send the missing pieces, and those will be tracked as well. So
you can know what didn't reach the destination, and you can resend
yeah.
that.
So TCP does that actually. Like it's defined by the protocol how an endpoint retransmits. So that's what makes it reliable, because you can have a way you have a way to communicate with the other end in a way that you can send all the data that you want to send and know when it's done. So you don't need to retransmit anything on top of it. So that's what makes it reliable. UDP is not. And that also makes it simpler and less prone to issues brought by things like NATs, network address translations. So one assumption that we made at this step is that every node has an address that's unique, and every node can send packets to every other node through its address, knowing only its address. So in the real world, it's not the case. So not all nodes have a unique public internet address, and that's not true for IPv4 because we have
Limited space.
a limited address space that's exhausted. So we don't have that problem with IPv6 because we have enough addresses. But that's not the topic. So then it doesn't, like, having a reliable transport protocol still relies on the assumption that packets will eventually reach their destination, both for UDP and for TCP when it comes, for instance, to the handshake. In order for a handshake to complete, you need bidirectional communication to be possible.
Yeah.
So what makes it possible is not only the addressing, the fact that you have an address to send packets to, but also what we call routing. So what we call routing is the incremental advancement on a path towards the destination in a way that's sufficiently well functioning that packets eventually reach their destination. So do you have any idea how routing is done?
No.
No.
I mean, I can imagine that this means just like finding the best path from A to
Yeah.
B, but how it is done?
Yeah.
Like a compass. Like there's a sort of.
I imagine
know
that maybe it
I
has
said that.
certain nodes, and then it has to go through that nodes, but I don't know.
Do you want me to give a less strawman, slightly educated response this time?
Sure.
Okay. Well, my understanding, and it might not be complete, is that like every edge has an idea of like where to send packets for which range. Like every edge has connections to other edges or like other entities in the network, and they know that if it's in this range of numbers, send it to this person. Otherwise, send it to this person.
So is it like some kind of
And that just happens over and over and over again until it gets to.
So it's like
So
many,
it's like
many.
so it's like a river and tributaries, effectively.
What?
Like you sort of a river. What's it called? Like a river system. You look down on from space and you see a river system, and at the top of it you have. So if you imagine the source of the data is like the top of the river, and ultimately at various forks it's like further channeled and channeled and channeled.
Exactly. That's how it's done. So at each fork, you will have to decide which substream
Substream,
to
But you know these
navigate.
spots where the river kind of
yeah. So that's
splits.
the thing. That's
You know the location, destination of that.
right. So that's the next complicated thing to shed light on. But before that, let's define what's a router and let's define it in a more rigid way.
Or exact.
Exact. Well, it's not exact actually, but so first thing first, something that you probably didn't know is that on the internet, every endpoint is a router. So your laptop is a router. So yeah. So every computer connected to the network, and that can be considered an endpoint. So that's the only type of computers that you are usually concerned about. These are your nodes. These are your clients, your servers, So I'm
And
not.
also routers.
So, yeah, of course, routers are
We're just
routers.
in the middle of the stream, but join the discussion
No,
about
it's
how
fine.
internet works.
Yeah, keep going. Actually.
Right. So yeah, every computer, every endpoint is a router. So, for instance, your laptop knows how to route packets that it emits. So all packets that it sends will go through what we call a route. So that's
Tributary.
so piggybacking on your analogy, there's a single stream, there's a single river that comes out of your laptop.
Yeah.
So it's the routing decision is very easy. All packets go through what we call the default route.
If we wanted to, could we plug in 2 Ethernet cables into our laptop and tell it like for this range of addresses use this route and
Yes.
this okay?
Yes, and that's something that you might want to do if you are using, for instance, a VPN connection and an encrypted tunnel. You may want to send some traffic through the encrypted tunnel and some other traffic through the unencrypted link directly without being encapsulated as a VPN packet. So
So sorry, in that example, you're splitting effectively. You've got two computers, like before you hit the mainstream, and so they're both filtering in. Is that right?
So there's no one mainstream.
Yeah.
So it's just that there's a single one coming down.
Yeah.
a usual the way a laptop is usually connected to the
Yeah,
internet.
yeah,
So you have a single pipe. The example I gave with a VPN connection is a bit more contrived in that one of the two streams that
It's
comes
inside
out
the other one.
is
Yeah.
is actually encapsulated
Yeah.
over the other one.
Yeah.
But it's in the way the routing works. It's exactly the same as if it
Yeah.
were two separate connections,
Yeah.
links. We say links. A connection is a different thing.
Mhm.
That's what we defined a bit earlier when we talked about TCP.
So stream is a connection, kind of.
So
Okay, yeah.
Well, if,
We
if
do-
we're talking about video streaming, it's usually UDP.
right,
Yeah.
exactly, yeah, because we don't care if we lose some of the data at some point. We just want to keep sending
Yeah.
data and not causing lag.
Okay, that makes sense.
Yeah, because if you transmit every time
Yeah,
packets are dropped,
Yeah,
then
yeah.
you will add latency,
Yeah,
which you do not want in the live stream.
Yeah.
So that's one of the advantages.
So,
of
so
UDP.
it's almost like you've got like TCP is finalizing to a
Yeah.
certain extent,
Yeah.
whereas you literally want the stream, and it doesn't matter if like you lose a bit in the stream as long as the stream continues.
Yeah, for UDP, yeah.
Yeah.
Yeah, that's why you use UDP. Yeah. So yeah, the simple case is you have a single what we call static route. So in the case that we discussed, so there's a single static route that is called a default route that all packets are sent to. So we discussed the second case in which we have a default route in which packets are sent to, and another static route that is defined by a block of destination addresses. So I don't really want to go into CIDR and subnets because it might be a bit confusing and might not add a lot to the discussion. But yeah, like a set of addresses that so that will be matched, and so if the destination address matches that set of addresses, then it will be sent down a certain network interface. So in the example where you have two Ethernet jacks coming out of a computer, each one of those Ethernet jacks corresponds to a network interface. So a route is defined by usually like 4 attributes. So that's oversimplifying, but
if we have like two computers on the same network, would they have the same route?
yeah. So
Because they use the same IP address, I guess, or something.
yeah. So
Everything is blurry in my head about.
yeah. No,
all
it's
this
alright.
network,
It's alright.
yeah.
It's alright. So the protocol that you use to send packets down the wire it's called is called Ethernet.
Mhm.
So it doesn't do routing at all. It's not about like it's a lower. It's just it's a lower level than what we were talking about. We're talking about routing. So layer 3 and up. So I'm supposing the OSI model, which is a model of encapsulation. You don't really we don't really need to go into it. It's just a convenient way to structure the discussion. So we're skipping a layer here. So if we talk about computers that are actually directly connected, then there's no need for routing, and we don't actually use routing for that. We just we use a different kind of address, which we call Ethernet addresses. You probably know them as MAC addresses. Yeah. So that's at the Ethernet layer. So
So
that's-
routing is only important when we're talking about the connectivity between peers that goes through ISPs.
Where the intermediaries, not necessarily ISPs,
yeah,
but
intermediate,
intermediaries,
yeah.
usually ISPs, yeah.
Okay.
So we are going from more abstract to less abstract. So no. So in any case, an application will use IP to join to join peers, to communicate with peers. So you will use an IP address, not an Ethernet address, even if the computers are actually directly connected. So let's get back to maybe we should go down all the way to the link layer. So that's what's below Ethernet. So Ethernet is what we use for structuring packets. So that's what defines what's a packet, not how it's transported, not how it's routed, but where it starts, where it does start, where it does end, and that's the unit of data that we transmit over the network.
So it's like a message.
It's a message, yeah. So the default size is 1,500 bytes. That's the size we usually work with.
Mm-hmm.
So that's probably, as you programmers, you probably have an idea what 1.5 kilobytes is.
Yeah.
So that's the default size of an Ethernet frame. We call them frames. We call them packets when we are just above in the abstraction layers. So and you can send an Ethernet frame to a Ethernet address. So you have to know the MAC address of the destination computer on the network, on the same network branch. So that's what you call the same network is not actually the same network, it's the same network branch. So you have only a layer 2 switch between your computer and the other computer. Do you know what you all know what a switch is?
Something like a router.
So on the above layers of abstraction, you can define a network of being made of two kinds of components: pipes and switches. So switches in that point of reference is a computer that decides where to send data and then just forwards the data. That's what we would call a switch in that reference, in that point of reference. At the layer that we're discussing, there is a difference between a switch and a router. Okay, so a router will operate at layer 3, that is IP, Internet Protocol. So when we talked about how your laptop is a router and can send packets through the network to an address it knows, global address it knows. So that's layer 3, and layer 2, Ethernet. You send data to a hardware address, so a MAC address, and so the destination has to be directly connected to the same branch of the network.
And this goes through a switch.
It can go through switches.
Yeah.
But
Or
layer
it
2
can go
switches.
directly if we don't have intermediary.
So in that case, all the intermediaries are under your control. Yeah. So for instance, computers connected to the same Wi-Fi access point, or connected to the same Ethernet switch, or connected to a series of Ethernet switches that are coordinated. But that requires a common policy, a common network policy So usually common ownership of the switches in order to work. Otherwise, there will be conflicts, loops, and other things that we don't want. We don't want. Yeah. Sorry about that.
It's okay. I mean, like, I'm going on a bit of a tangent here. So I am curious if you know if the terminology is borrowed directly from telecoms, where like switches
Yes.
back in the super early days were literally like people at a board of
Yes.
yeah
Yes,
cables.
That's exactly what I was going to ask.
Yeah.
That is exactly what it is.
Yeah.
So that's the same terminology, and what we call the switch in layer 2 is exactly what the telephone switch used to be, and with an operator that does the
switchboard.
plugging.
Yeah.
That's the switch. That's what we call a switch. So in that case, all the switch operators in a telephone network have to be cooperating in order for the system to actually be able to
Otherwise, you have a loop or something.
you can have loops. Yeah. So that's our layer 2, and that's what we use that we generally use to connect computers directly one to another. It doesn't allow transitive communication. That's
So switch is layer 1.
layer 2.
Layer
So
2.
layer 1 is the physical layer.
Yeah.
So that's
layer 2 is the layer 3 is the router. Layer 2 is the Ethernet and the switching. Is that right?
Yeah. And layer 1 is the physical layer. So that's your network cards. So that's your Wi-Fi chip and its radio, its antennas, and the electromagnetic radiation that compose your radio communications when you do Wi-Fi, or the fiber optic cable when you do optical communications. That's layer 1. That's the physical layer, and there are a variety of ways to transport information. You can do Morse code, you can do carrier pigeons. Literally, yeah, you can.
Morse code, like, but not. This is going to be a really stupid question now.
Yeah.
Like, but Morse code, like, there's not a Morse code system within our computer that still works.
No, there's not.
No.
But you can program it. You can do it.
But that's not like a primitive, some like way down primitive. That
No. So the fact that it is its own layer is that it's a whole series of protocols and systems and hardware and ways to transmit data. So you can use Morse code if you want as a physical layer, but you're not required to. So the way we do it is usually radio for wireless communications, modulated lights through lasers for optical communications, and modulated carrier wave electron electronic communications for wired copper interfaces. But which physical layer you use doesn't impact in any way the function of Ethernet. Yeah.
It's just the onboarding.
Yeah, it's the physical part of it.
Yeah.
And as long as you can send a frame that will be interpreted. Thank you. Correctly by the other end of your pipe, then you can do Ethernet.
It's agnostic.
Yeah, it's completely and each layer we've been discussing is agnostic.
The other layer.
To the
Which is obviously what like XCM and XCMP is trying to be. Is it?
Yes. XCM. Yes. But that's.
I think we lost someone. I'm sorry about that.
We'll be back. Nina's back.
Okay.
Oh, it's power cable.
Oh yeah.
She wasn't bored.
I thought you were.
Oh God.
Sorry.
You're talking about Morse code.
I didn't want
Because
to
you went-
interrupt.
because it's gone press technical. Right?
Oh, it's
Yeah,
fascinating.
that's
So-
why I don't know it, because it's usually so
Yeah.
hard, because you need to build a whole mental map.
Yeah.
It's exactly what
But-
it is, isn't it? It's a metaphor, a metaphor, a metaphor.
Yeah.
Yeah, but
Yeah.
now you have to
An
keep
analogy.
all these metaphors
Yeah.
still, you know.
But it's a
That's-
very old and well known metaphor now, which is
Yeah.
just the OSI layer.
Yeah. So we've gone through the whole like skipping some steps, but the whole OSI layer. So that's basically how computers communicate. Now, the missing bits is how everything is coordinated when there are multiple independent intermediaries. So
Yeah.
that's the thing that we didn't discuss,
Yeah.
because once we know all that we've been discussing, we know how computers communicate over a network. Now there's a very important part is how we coordinate independent entities that operate under their own law or policy, what we call policy.
But they need to follow the same standards to make all this happen, I guess.
So in a way, for their direct communications, they do, right? But
Internally, they don't.
Uh-huh.
internally they don't.
So they just have to know how to accept and
Yeah. So, yeah.
understand the information, but what they then do with it is...
So then, if we consider a network that's larger than just a series of switches that directly connect computers that can address each other via their hardware address.
What could that be? Like some example?
So, for instance, let's say we have we have the Astro chip
Yeah.
connected.
To all of our devices.
Well, yeah. So, that's the way it's done right now is.
Because he built actually
it's-
the
it's-
network.
Yeah, it's a very simple network. There's a single layer 2 for everyone, so all devices can address all other devices via their hardware address. So we have the concept of broadcast as well. So you can also send a frame, a UDP packet to to all the participants on the network. So that's how we discover the hardware address of a device, given its network address, IP address. Network address is IP address is a network address, and MAC address or Ethernet address is a hardware address. So if you know the network address of a device, the way we do it is that when your computer connects to the network, it will broadcast the fact that it's connected, and when it wants to reach another device that it does not know about, so that has joined the network before it could knew.
Before, they broadcasted when they joined, but then the other one joined
Yeah.
after, so it couldn't.
So you don't know about the ones that joined before.
Yeah.
So for that, you will broadcast a message that will ask who has this network address. So I want to reach a device which has IP address 3. Which device has IP address 3, and you broadcast that.
Because the hardware device and network device, the hardware address and network address are not the same.
They're not the same.
Yeah,
They're not the same. So yeah.
And do all of our computers in the network, are they all aware of all the other devices in the network?
In the same branch.
Yes. So my computer now is aware of all
Yes,
the Astro chip computers.
Do you run Linux?
Yeah.
So run IP neighbor
In
in your
terminal.
terminal. IP space neighbor, NEGIH.
OR or OUR? Native?
OR. So yeah,
American.
we use American English for all that.
Okay.
That's the standard.
I see 1, 2, 3, 4 or something.
Yeah,
and
one is IPv6.
Yeah. So you see, your computer knows about 3 devices,
Mhm.
all connected through your Wi-Fi interface. LL address is link level address. So that's your Ethernet address.
Mhm.
And you see network address,
Yeah.
network address, and reachable. Okay, so you can reach it. You just have to send a frame over the network.
So
to
I could send a direct message to any of
Yeah.
those.
and you have also
What is the last thing?
so that's an IPv6 address, and that's the IPv6 router. That's on the network.
Interesting.
So you as you can see, just as a quick aside, you have 2 network protocols, 2 internet protocols implemented in your operating system. That is IPv4 and IPv6. So they use the same Ethernet addresses, but they use a different format for their network address.
So do I get this written down twice? Once with IPv4 and once with IPv6?
Well,
This information, IP neighbor?
yeah, so it's presented in a unified way, but in practice, they are actually separate tables.
Uh-huh.
So that what you can see here is your ARP table, or ARP, for IPv4, and neighbor table for IPv6. They are separate, different tables, different. So that's what your computer looks up in order to know where to send packets. If it doesn't know about if it can't find a directly connected computer at a certain address,
Yeah.
we will use routing. So if you type IP route,
Mhm.
you will see your routing table.
Mhm.
So your routing table has a few entries.
Mhm.
So the first one is your default route. The second one is an auto discovery protocol that's used for like, let's not talk about this.
Yeah. It can be a rabbit hole.
Yeah, but it's irrelevant for what we're doing, what we're talking about.
Good
and-
that you can
yeah.
make distinction what is relevant and not.
And the last one is a static route for the local network. So all that's in the local network, it will be sent directly to its destination. Everything that is not will be sent to the default route, which goes through the router that's at the edge of our network.
Mhm.
And that knows how to send packets to computers that are beyond our network.
Interesting.
So that's what we call a routing table. It's a very simple one, and but they can get much more complicated than that.
Based on the size of the network, or
No, it's no, because it's based on the number of links that we maintain to the outside. Here, it's very simple, very, very simple. We have a router that knows how to send packets to the whole world.
Mhm.
How? It's very simple. It sends all the packets to British Telecom, which will then take care of all the routing and stuff like that.
So it has only one way out,
Yeah.
and
I can give you an example of something that might potentially be more complicated. I'm planning on having a system where I'll have a Starlink
Yeah.
and
will you?
an ISP, normal traditional ISP connection. So it'll be both of them connected. So I'll have 2 WAN connections on my primary router, and also a bunch of other routers throughout the device. So imagine, like, would the routing table change in that scenario if, like, a device moves through the house, so to speak?
Okay, so whose routing table?
the routing table of the router,
Which router?
the primary router.
Which is connected to what connection?
It is connected to both of the external connections and also several other routers. It's like
It's
the hub.
switching between. It cannot be connected to two at once, right?
It can.
Ah,
Of course it can. Yeah. So
Of course it can. Really, you can be connected to two
ISPs, yes.
Really?
Yeah.
To make sure that it never
You might have two public two public addresses.
exactly, and so there are several ways to do that. So the simplest way would be to have a bunch of static routes, which indicates to the router, which set within the global address space of the internet of addresses, which set of addresses will be sent to Starlink, and which set will be sent to the other ISP. So that's static. That doesn't change. Doesn't change dynamically. I mean. So that means that if Starlink goes down, if a space debris collides with the satellite and then Starlink is not reachable, then half the internet for you
Is inaccessible.
will go dark.
Yeah.
You can't reach it. So that's one way to do it. It has an obvious drawback. And then we'll introduce the core of this discussion, which is what we call dynamic routing. Ooh. Ooh. So that's the actual engineering prowess behind the internet. It's how we coordinate dynamic routing. So dynamic routing is the practice of changing the routing tables in a way that adapts to the conditions, the operating conditions of the network. So if Starlink goes down, send all the traffic to the other ISP. That's what we call dynamic routing. So that's actually much more complex because how do we?
Yeah, when do we use static and when dynamic routing?
So
Because some networks they just have static, or is every time dynamic?
So most network will use both. So yeah. The answer is it depends.
Static for things that are static in your network.
Exactly.
Dynamic for things that you don't know necessarily.
Yeah, exactly. Exactly. So, for instance, if you have like the way it's usually the way that that scenario is usually plays out is that instead of having a single router connected to Starlink, you will have two with two antennas, and if one fails, you will send the traffic to the other. So in that case, the routing table doesn't change. It's a static route that you will use. It's just that the second router will take over the IP address of the failing one. Just detect that the other one is down, and
Are you talking about like the local IP address? Oh no, this is both of them are Starlink.
Yeah.
Yeah.
So you'll have only a single public address for the two routers. One is active, the other one is not. And if the active one fails, the other one can detect that by sending keep alive packets and communicating constantly with the other router. And as soon as the communication doesn't work between the two, it will.
So they're constantly pinging each other to know if they're.
Yeah, that's what we call a keep alive.
Keep alive.
Yeah. Oh, that are other words, but yeah.
Yeah.
Let's not get into.
Yeah, but constant pinging.
Yeah, constant. Yeah. So, yeah, and so in that case, the route won't change. So that's still that should be a static route. But if the problem is on Starlink's end, then you can't detect it that way. And you're not in control of who routes your packets on Starlink's side. You only control it on your side.
Yes.
So then we use a dynamic routing protocol. So If the link in question is an internal link, we will not use the same protocols to do dynamic routing as if it's another entity that is responsible for the potential failure or change in topology. I mean, like it could be also just adding new routers with new routes, not necessarily a router failing. So the internal dynamic routing protocols are not of much interest to us, but I mean, besides knowing that they exist.
That'll be for like roaming devices.
Yeah. For instance, or just large networks that change topology often, or have failover mechanisms that justify routing packets differently.
Within the network.
Yeah, if like imagine being an organization that controls multiple fiber links, and one of them is cut, you might want to use a less efficient route, but that works, rather than sending packets through the one that's the more direct, the most direct, but is cut. So that's why how protocols like ISIS or OSPF, for instance, are used. If you do mesh networking, radio meshes, you would use another set of internal dynamic routing protocols, but that's a very that's a good use case for studying internal dynamic routing protocols. So they are used to distribute changes in the routing table in an organization that has the same routing policy. So it's your own shit that changes. You want the rest of your own shit to know how it changed, and adapt and choose the best path for down which to send the traffic.
So these kind of neighbors and stuff, they need to know what are
They need to gossip about.
Yeah. So large subset of internal routing protocols do gossip. They are actually gossip protocols, and that's where gossip protocols come from.
Yeah.
They do not come from
people gossiping.
Well,
in a way they do, but yeah, no, it doesn't come from the peer-to-peer network world or second scuttlebutt or stuff like that.
This is the first time I heard about it.
The first use case of these protocols is actually dynamic routing for internal routing, so within an organization, and so and then there's the external routing protocols. So the one that's used to the one that's used to distribute changes in the routing tables between two other organizations. So these are the intermediaries that will route traffic for other organizations. So either because they are the destination. So if you visit Starlink's website through your Starlink connection, you will still have to go through a border router from on your end and on Starlink's end. So, by the way, let's introduce what autonomous systems are.
What?
Autonomous systems.
Autonomous system. Okay.
So an autonomous system is a network that operates over a single routing policy, a common routing policy. So, for instance, your route, in your example, in the way you imagined it, your router connected to Starlink is part of Starlink's autonomous system. Okay? It's because Starlink decides the routing policy of your device.
But in the like that's if it's like a single
Yeah.
WAN, not a dual WAN.
Yeah, but if it's a static route,
Okay.
then
Then it's
still on it's still on to Starlink to decide
Yeah.
how the packets that come out of this device are routed.
Mhm.
It can be multi-homed, but well, so if you want to so the way you didn't imagine it and the way you would have to do it if you want to achieve what you want to achieve is not the same way as connecting to an ISP the regular way.
Mhm.
You will have to connect to the ISP as a peer,
Mhm.
because now we're introducing the notion that the internet is a peer-to-peer protocol,
Right.
but the peers are not computers.
But
The peers are
autonomous
networks,
systems.
they're autonomous systems, indeed. And so, if you join the network as a peer, then it's very different. You won't you will be able to distribute routes
Mhm.
to your peers.
Yeah.
So-
So I can say behind me there are
Yes,
this range of addresses.
exactly.
Yeah.
And how do you join as a peer?
So we use a protocol called BGP, the Border Gateway Protocol,
Oh.
for that.
This is no before we were talking about it.
Yeah. So we've almost gone full circle now.
Ooh.
So for that we need a few things. So first we need a router. We need
Which is any computer, you said, can be a router?
any computer can be a router. Any internet capable computer can
Yeah.
be a router. We need an autonomous system number that is unique, and that's attributed by a registry.
Which registry?
Registry.
Yeah, which one?
Oh, so here we're in Europe. So our regional registry is the RIPE NCC.
Mhm.
So that's the Network Coordination Center for Europe.
And where do we get it from? Like, how does it come to us?
So there are a few ways. So one way is to be a RIPE member. So to join RIPE is.
So he will have to do this.
Yeah. So it's a just basically a administrative thing. Right.
So you fill out the form.
You fill out
and
the form.
Register basically.
There's a fee for joining. That is about €2,000.
One-time fee.
It's a yearly fee.
Jeez.
Yeah.
Wow. Wait, what is the benefit of this now?
So then you're a member of RIPE. So then you can access the resources of the coordination center. So the coordination center will include you in their effort to coordinate the network in Europe, the internet in Europe.
Mm.
So, and it will do so directly. So you can request autonomous system numbers, as many as you want.
Mhm.
If you want to manage several autonomous systems through a single organization, you can. And very importantly, IP address blocks, IP addresses.
So you technically become a provider in a way?
Yeah, you can become you can just be your own internet service provider if you want, or you can provide service to others. It doesn't change anything from the right perspective. For them, it's the same.
So I imagine that there are RIPE members who you can ask for your autonomous.
Yes, so that's the second way of doing it.
Mhm.
So if you are a client of any RIPE member, that is called a local internet registry. So that's basically your data centers, your ISPs, your any large organization that is a RIPE member. So I'm talking about RIPE because we're in Europe, but each region of the world has its own regional registry, and so each member that is selling internet services can be a local internet registry. So they can proxy requests for autonomous system numbers and internet protocol address blocks, so IP blocks.
Are they also some sort of a switch in all these kind of big global?
Right? No, they are just coordination centers. They only do the administrative stuff.
So, throwing back to our earlier off-stream discussion, I said, like, why can't these coordination centers be blockchains? And you said there's no need for them because we don't have to trust the autonomous entities. So there's no, like,
Need or what?
yeah, there's no reason they need to be anything other than centralized entities. But from what you're describing, I see a lot of automation benefits and a lot of, like, cost reduction benefit.
Oh, wait, let me finish, because
Okay.
I didn't fully explain the second way of obtaining an autonomous system number and internet protocol address blocks. So, if you go
We're in
through
the kitchen, so if anyone is wondering what is beeping, it's a dishwasher.
if you go through a local internet registry, you do not need to be a right member. You just need to have some sort of agreement with a member of the right, which needs to pay the fee, but you don't need to pay the fee. So, and then
They'll probably charge you a fee.
they could or not.
Or not.
It's just a number that's assigned. It has no value in itself. So,
But you go then through them somehow?
yeah.
Uh-huh.
So the way it's usually done is that, in order to connect to the internet as a provider, you will need some sort of physical connection. There's matter at play here, and it's the providers of these services in the physical world are all members of the regional registries, and so they will basically provide numbers to you and for no additional fee, because you already have a usually commercial relationship with them through the cross connects, for instance. So the cable that goes from your routers to the internet exchange point switch, for instance, or the cable that goes from your routers from your router to your peer routers, or the entity that installs the antenna on the roof of your building for a radio link. Or so, for instance, you could. I don't know how Starlink does it, but if ISPs wanted to obtain numbers through Starlink, they could probably ask for ARIN, which is the American regional registry. So they could probably ask Starlink, hey, I want a BGP session with my link, with my connection. Send me a default route. So the way BGP works, so yeah, replaced with blockchain, that could probably be done, but it doesn't solve any real problem, in my opinion, at this point.
I mean, what would be the problem? Like, okay, we have to trust this registry, but can they abuse the power, and for what, and why would they?
I mean, the problem I see is, like, there's probably some benefit to having the autonomous, what's it called, number.
Autonomous system number, yeah, you can be a peer.
Yeah, you can be a peer. There are places in the world where the local ISP or the local registry member will be instructed not to give you a peer number because that's a licensed activity or something like that.
Or like in Myanmar, when they just shut down the internet service providers, so then it would be beneficial that somebody else could.
We're talking about the service providers themselves. and the way they coordinate. So if a government wants to shut down the internet, they
Yep.
shut down the service providers. They do not shut down the coordination center. And the coordination center is operating at the scale of a continent. Also, once the number is assigned, it is entered in a registry, and then it doesn't need to be. There's no active. There's no active work from the registry besides the registration.
But what would happen if they refuse putting you on in the system or
you
on
you
the?
go to another registry.
But you said that there is only one in Europe.
Yeah, but you can.
You can go to American.
Yeah,
Even if you're based in Europe.
of course.
Huh.
It just doesn't make much sense.
So it's more like a mastodon than the centralized system. So it's more like a distributed,
It's a federated system.
federated.
It's a it's not a centralized system. It's hierarchical, but each level in the hierarchy is
Equivalent.
kind of a federation.
Yeah.
It's not really a federation because the level just on top of it in the in that hierarchy defines which blocks of AS numbers and which blocks of IP addresses go to which registries. So it's hierarchical, and there's a point of centralization, which is the INR, which is the internet.
Domain. Is it for domains? No, it's not for domains. Protocols, or no?
So that's the Internet Assigned Numbers Association, the INR, and ICANN, which is the Internet Corporation for Assigned Names and Numbers. And if there's a point of centralization that could be a problem, it would be that one.
Yeah.
So these two entities, which are the point of centralization, that could be a problem. But the regional registries or the local registries are not or not in themselves a point of centralization. It's the way they are organized that relies on a central point, and that's what could be a problem. But below that, it's basically the equivalent of a federation, and again, it's just for assigning numbers. It's not a right to participate in the internet.
Because you can participate as long as you have a connection.
Yeah, and if you want to make up an autonomous system number that is unregistered, and everybody that you are communicating with recognize that as yours, then it's fine. You do not need. There's no technical need to have that. It's just a convenient coordination.
I can give a analogy from the Polkadot and Kusama ecosystem, which is that like in Polkadot and Kusama, every chain has a different address format.
Yeah.
It's just a visual thing that like disambiguates between which network you're communicating on.
So it has a public key, kind of?
Yeah, it's a public key, and then there's like a prefix to the public key, but that prefix doesn't tell you how to encrypt it or anything. Like it's not relevant to the communication really. What I'm imagining is it's not like that, but like the method of assigning those numbers is the same, where it's just like a GitHub repo where you put a name, but it's not like that. But
That's correct. And for instance, that there's a that if you want to know more about these things and dig deeper by yourself, have a look at what DN42 is. So
DN42.
yeah, so DN42 is the acronym for Decentralized Network Number 42, which is a decentralized version of the internet. So without that point of centralization that we discussed, so there's no INR and there's no equivalent of INR or ICANN within DN42, and those two entities are basically replaced by a Git repository.
oh, okay.
Yeah, that's and it's a darknet.
Mm-hmm.
What we call a darknet is that it's not reachable publicly through the internet, So you have to have a link with at least one peer within the network in order to join it. So that's what makes it a darknet. Not much more than that. There's no darkness in it. And it's a project that allows regular mere mortals to use and experiment with these protocols and technologies. They are at the core of the internet backbone. So that's not something that normal people actually manipulate and work with. But they are open protocols. You can use them. It's just other than for learning, but for learning purposes, it doesn't make much sense to play with them if you're not connected directly to the internet.
Yeah.
So,
I mean, what I'm familiar with is CJDNS.
yeah.
Where is it like also? Would you say that like Hyperborea, which is like the main network of CJDNS peers, is also a darknet?
No, because
It's also bridge over.
oh wait,
bridge.
no. CJDNS. I think CJDNS is a darknet. I'm not sure. 100% sure. I'm not getting confused with another project. So it's not an alternate route, DNS route, right? It's an actual encrypted network.
Yeah.
So that is a darknet.
Yeah, and
there's as long as there's no public internet way to communicate with it, we can call it a darknet.
the interesting thing I find about it is that it assigns IP address blocks by public key.
Okay. Yeah.
Instead of by GitFlow or organization or something.
Yeah. So these are alternate ways of doing those aspects of the internet that are highly centralized, and it's important that they exist because it kind of keeps the system honest, but in a way. There's no real need to migrate to them in order to reap the benefit of that, because keeping the system honest is enough, because if the system starts not being honest, then it will basically destroy itself.
Mm-hmm.
Because that's the whole goal of that of these parts of the network is ensuring coordination. They are not participating in the network in any other way. They are not making policy. And if they start trying to make policy, then we will change policy. We will find other ways, like CJDNS, for instance, to assign names and numbers, or to decide how we allocate numbered resources. But again, they're numbered resources. They are not supposed to have any value.
Mm-hmm.
They are, because the internet is an open network. That is, you do not need permission to join the network. Just some paperwork that is systematic. That.
So they literally kind of work as a ledger.
Yeah. And it doesn't really need to be as secure as a financial ledger, for instance, because there's no value involved.
Yeah, the only thing what it could be, it could just like take this administration away and make it like, I don't know what they check. Do they need to approve? Or is it just like, okay, we will put you on, then it's just like a waste of money maybe, because it could be just automated.
Well, they basically prevent spam.
Yeah, and this is what blockchains do with the transaction fees, kind of.
Yeah, but again, like as the stakes are not the same as what we use blockchains for, that's why I do not think that it's necessary in the current form of the internet.
Mm-hmm.
Again, that's not something absolute, because we talked about IPv4 and the exhaustion of address space. That changes that dynamic drastically.
IPv4 has value now.
IPv4 address space has value now.
Yeah.
And so, but these are global systems, so they take time to change.
What did Macintosh say last time? What did they do with this? How did they try to extend IPv4 number of addresses? There were some techniques that were used. I don't know. I don't remember.
So the most common way to extend the address space is NAT.
Maybe that's
So network address translations. The thing with NAT is that it breaks a lot of fundamental assumptions that we make as users of the network. So that's why you have to do NAT hole punching and do these kinds of voodoo magic things in order for your nodes to communicate directly on the network that's supposed to be peer-to-peer. So that's the result of artificially extending the lifetime of IPv4 because basically the world isn't quick enough to migrate to the next version of IP. So the correct technical solution to the exhaustion of IPv4 address space is to migrate to IPv6. That's the best way. It's not the most practical way because reasons, but technically it's by far the best way.
I mean, this IPv6, this migration discussion has been happening for decades now, right?
What?
Yeah,
Is it decades already?
1 decade.
One
A bit
Whoa.
more than a decade.
I thought this is now like a new thing. Last month.
No.
Oh my goodness.
That's the 10 to 12 years, I'd say. That IPv6 is considered stable and ready for production.
Wow.
It works.
But what is IPv6 or 4? Are these protocols or what is this? Why does it need to be stable?
So that's the internet protocol. So that's the network protocol. We discussed the different layers that we traverse to for computers to communicate with one another. So the one that defines what's an IP address, how routing is done, what a route, what's a static route, all that's IP. Also, how to translate hardware addresses to network addresses. That's part of IP. That's the core part. That's the core part of the internet. That's the part of the internet that allows.
Makes it internet.
Yeah, exactly.
Yeah.
So that's
Okay,
yeah.
then it's understandable that it takes time to transition to the new protocol because we don't want to break everything. Okay, this makes sense. Should we slowly wrap it up?
Yeah.
Any final thoughts
So
or suggestions?
just a very quick quick talk about how BGP works because it's very simple and it's deceptively simple even. So when two ISPs are connected, have edge routers connected to one another, they will establish a simple TCP session between the two routers and send routing table changes to one another. And so the routing tables that are sent through BGP are not exactly the same shape as the one that we saw on your computer. They are not just a destination address and next hop and an interface. They also have what we call an AS path. So that's a list, an ordered list of autonomous system numbers. And that's a projected path to reach the destination. All right, and that's what's used to select the best route. And I'll not describe how we select it, but we need that information.
You would have a rough idea of which IP address you want to connect to and which AS they're part of.
Yeah, and which AS are in the middle, which ASs are in the middle.
Yeah.
And we can manipulate that by doing what we call AS prepending. So we will, in order
Put
to
our own ASs in there.
yeah, like add it multiple times in order to make some routes appear longer than others. If we want to direct traffic more one way or more another way, That's basically how we influence the routing decisions through BGP, so that we can basically tell Starlink, no, this link is slow, so I will send an AS path that has 4 times my ASN, so they will not send packets my way through this and this link, but rather try and find another route before they do that.
Would you say a concrete benefit to having your own AS number is reliability in connections with you?
Yeah, if you want to do multi-homing, so if you want to have multiple paths that connects you to the internet, you basically need
AS number.
an AS number and BGP and all that. Otherwise, you have each address on your network will be served by a single link, and if that link goes down, then those addresses are unreachable.
Offline, yeah. Interesting.
So if we now summarize it as for a 5-year-old, how, because like I understood parts,
Yeah.
but now my mental model still doesn't work.
Okay.
Just to kind of, but very, very simply, so peer-to-peer using IPFS or hypercore or SSB, through what hubs does it go exactly?
So we have a complex stack of protocols
Yes.
that are used to address and connect to other devices over the internet. And a critical point of that stack is a very simple protocol that relies on mutual arrangements between participants to exchange routes and to route each other's traffic for no other reason than mutual benefit.
So you could technically even close this on your computer, disable
What
routing, or
you would have no access to the internet if you stop routing.
okay. Okay, sorry.
So yeah, we didn't go to the social structure of these agreements, and because I got kind of caught in
Other useful information.
Yeah, caught on the technical aspect of it, but whatever. So yeah, there are multiple protocols, multiple concepts, some pretty complicated, some less complicated, that come into play in order to provide that illusion that all the computers on the planet are directly connected. And it's a very diverse ecosystem of technologies that are a commons that we all have to maintain collectively in order for this network to continue functioning. And so it's important as protocol developers and protocol designers to understand how it plays out in order to be a part of the effort of maintaining them and making them sufficiently reliable and simple that they can basically be abstracted away in higher bits of the stack. And if you think of the internet only at the IP level, everything that's below can be completely abstracted away. It will work, whether it's carrier pigeons or lasers through fiber optic cables or Morse code or whatever. It will work the same. You don't really need to know how it works in order for it to work. But if you understand it, then you can be part of that stack and move that limit of the abstraction a bit higher and include your protocol and be a designer of an internet protocol.
Wow.
Yeah.
Just one more thing. I know it was such a good thing to finish, but I now have a question.
Sure.
Like, you know, like with these local first protocols, like I don't know, for hypercore protocol, I often hear that it's a local first protocol. And the way I understood is that like you can literally just connect it device to device. It doesn't have to go even through the internet service provider.
Okay, so see, remember when we looked at your routing table, and there was a route, and I said, let's not bother talking about this. Right, it happens there. That's how we do local
so it
first,
is possible, and
yes, and it's implemented, it works, and that's how we can do local first network protocols on top of all that.
Okay, and this is when basically these protocols are creating a censorship resistant
so that route that you saw is the route that's used to communicate with computers that are that you would connect directly with a cable, for instance, from your Ethernet jack to their Ethernet jack. Right.
And you can also do it through Bluetooth?
Yeah.
Because I think that...
for Bluetooth, it'll be a bit different. You won't have IP over Bluetooth, so you do that on the application layer. But if you do IP, that's the zeroconf and network auto configuration. That's the address that 169.0. So that's what you would use to do IP over a direct Ethernet connection without switch in the middle, without manually configuring an IP address on your computer and on the other.
Okay.
So Bluetooth would be different. It would be handled directly by the application itself, because there's no IP address. There's no we do not encapsulate IP over Bluetooth. It would be too slow.
But it's also possible.
But it's still possible, yeah. Just sending application data directly over the waves.
Cool. Do you have any?
So Bluetooth has MAC addresses. It's not Ethernet. So that's why I made the distinction between MAC address and Ethernet address. With Bluetooth, there's no Ethernet, but there are hardware addresses, MAC addresses, that you can use to directly communicate with a paired device. But you need pairing.
Cool.
Or BLE, or with BLE, you don't need a pairing, I think. I'm not sure. I'm not a Bluetooth expert.
I mean, I think like some people, it's basically communicating directly via Bluetooth LE is just a side channel where you change your name repeatedly or something like that.
I heard that the new project where Dominic Tarr is engaged in socket supply, socket SDK, SSC, so it's not SSB, it's SSC. They kind of are planning or having already this kind of peer-to-peer connection that can go also through Bluetooth.
Application there, as you mentioned.
So, for instance, that's a very, I think, a good way to wrap it up, actually, because that's one reason that makes it very important to understand how the lower levels of the stack work. Because in the case of Bluetooth, for instance, we don't have all that magic. So if you want to use Bluetooth for peer-to-peer communications, you have to implement these things yourself. So you have to understand that you have a network layer, you have a link layer, and you have a physical layer under that. You can establish sessions, and etc. etc.
So you cannot rely on any of this?
No, because it doesn't exist over Bluetooth.
Okay, but then you know that you're completely independent, that you don't rely on any of the existing...
Exactly. Well, there's, Bluetooth defines some of it, but in a different way. It's not internet. So,
Sweet.
You can connect to the internet over Bluetooth directly. You would have to have some kind of software that does the routing.
And this is what they're building, actually.
Okay.
Sweet. Thank you so much. I mean, it's hard to wrap my head around, but it's kind of nice to have, some of the ideas now floating somewhere. But now I know what I can read more about.
That's a whole new word for a protocol developer to so we couldn't go into detail in a way that makes everything clear. But I've tried to give you a rough sense of what lies in that darkness. Like
Yeah.
you can't have a clear picture in a couple hours,
Of course.
I think, or maybe
One
you could,
hour.
but
No, it's hard. Yeah.
but yeah, like at least you have the general shape of the thing,
Yes.
and where the points of centralization are, which are the important protocols, which are the cornerstones. Yeah.
Sweet. Thank you so much,
You're
really.
welcome.
Bye bye, stream.